Okay, so let's take another example just to kind of show you what I mean. Okay, so here we have a reaction. We have 2A plus B plus 10 joules making 5C. So right now, right away, we can tell this is an endothermic process, right? Our delta H is positive 10 joules from looking at this. Now, so this value here is the enthalpy change for this reaction, right? So the enthalpy change is 10 joules, positive 10 joules. But we can't call that the molar enthalpy change for everything here. Okay, so technically, it is only the molar enthalpy change for B, because B has a coefficient of 1. So molar, I'm just going to use delta H instead of writing enthalpy change every time. So the molar enthalpy change for B would be 10 joules per mole of B, correct? Right, so the coefficient is 1. If we wanted to determine the molar enthalpy for A, molar change in enthalpy for A, it has a coefficient of 2. So what that would mean is this 10 joules is represented for 2 moles worth of A. If I wanted to show only 1 mole worth of A, I'd essentially have to half that. Because 1 mole of A would be 5 joules, 2 moles of A is 10 joules, right? It's actually all about ratios here. So you're looking at a molar ratio. It's just you're using an energy value to compare it with, right? So for us to do the molar enthalpy change for a mole of C, C is currently showing 5 moles. So this 10 joules is represented for 5 moles worth of C. So that means if I wanted to show only 1 mole of C, I would have essentially have to divide that number by 5. So by having this piece of information, like a balanced chemical equation with an energy term within it, this is huge. We can get molar enthalpies for everything that is here by adjusting it accordingly. And of course, we can determine if it's endothermic or exothermic. So just be mindful of this if you're looking at a reaction and they tell you the delta H. They're giving you a lot of information there. And keep in mind, it doesn't have to be written in the reaction. It can be written beside it. So maybe the delta H of the reaction here is 10 joules, right? So it can be either in the reaction itself, written as a reactant or product, or it can be kind of written to the side. But regardless, this reaction delta H is for the entire process. Okay, so here is our formula. So we've actually been using that to do these example calculations without even really learning the formula yet. So delta HR is equal to N times delta HR naught, okay? So this value here with the naught symbol is representing molar enthalpy, okay? So notice the unit is kilojoules per mole. Your number of moles, of course, is represented by lowercase n, so that should be familiar from grade 11. And of course, the enthalpy change for a reaction is just simply in kilojoules. Now, sometimes this number can be the same if it's for 1 mole. So I'll go back to this. 1 mole of B is exactly the same as what is already being represented here. So it doesn't necessarily have to be different. It all depends on the mole value that you're working with. All right, so let's take a look at an example calculation here. And actually what I'll do, if you want to give this a shot, so first of all, actually, let me go back for a second to just remind you. So this value here, a lot of the time, you can actually look up this delta H naught, like the molar enthalpy values. They're found in your textbook. So those reference pages that I asked you to save as a separate file, it's in there as well. It's on page 307 in your text as well. So for example, molar enthalpies for combustions, there's a lot of them that you can look up. So this value, if it's not given to you, typically it's something that you can actually look up to solve the problem with. Okay, so let's take a look here. So what is the expected enthalpy change? Okay, so we're looking for delta HR. So notice they're not asking for the molar enthalpy change. They just want the enthalpy change. If we have 100.0 grams of methanol that's being vaporized, and it's telling us the molar enthalpy of vaporization for methanol is this. So this last sentence, let's say this wasn't here, you could possibly find this in your textbook as a reference number, but regardless, it's here, so we don't have to look that up. So we're looking for delta HR, right? We have the mass of methanol, so it's 100 grams, and we have the delta H naught for the vaporization, so that is 39.23 kilojoules per mole. Okay, so let's take a look. So our formula is delta HR is equal to N times delta H naught. So we have our delta H naught, we're looking for delta HR, and then moles, well, we have the mass of methanol, so we can solve for the moles of methanol. So moles is mass over the molar mass, right? So if you remember from grade 11, I use lowercase mm, or, right, you can say capital M for molar mass. So the unit for mass has to be grams. A little quick review. Molar mass is in grams per mole. So solve for N. So moles is going to be 100.0 grams over the molar mass for methanol. So methanol is CH3OH, which we should remember from our organic chemistry unit. CH3, my 3 is not looking good. 3CH3OH. So you're adding, remember to get the molar mass, you look up on the periodic table the atomic masses for each one of these. So we have 1 carbon, we have 3 plus 1, 4 hydrogens and 1 oxygen. So altogether, this is a molar mass of 32.05 grams per mole. Okay. Now for molar mass, I typically don't keep more than 2 decimal points. You can keep more if you prefer, if that's what you're used to doing, but I would not round this to less than that. Okay, so it's like the minimum numbers you should have here. So 100 divided by 32.05, we get 3.1201 moles. Okay, so then at this point, we're just plugging in and solving for delta HR, right? So we have our mole value now, and we have our delta HR. So it's going to be 3.1201 moles times delta HR, which is given to us in the question, 39.23 kilojoules per mole. Kilojoules per mole. Okay, so what happens here is the mole value cancels, and we're left with units of kilojoules. So here we will have, let me just work that out for a second. Okay, so we should get a value here of, let me get my pen back, 122.402 kilojoules approximately. And then we have to bring back our significant digit knowledge. So going back to the original question, 100.0 grams is 4 significant digits. Okay, I will tell you that when you are using a standard data value, so this molar enthalpy is actually not being used for significant digit data because that is a constant. So the only number we really have to go by here is 100.0, which is 4. So your final answer here should be 122.4 kilojoules. Okay, and notice, right, it's a positive value. which tells us that this process of vaporization for methanol is an endothermic process, right? So if we wanted to vaporize, this should kind of make sense. If we wanted to vaporize 1 mole of methanol, it would be 39.23 kilojoules. But we're not vaporizing 1 mole, we're vaporizing 3.1201 moles. Right? So you have to adjust your kilojoule quantity dependent on how many moles are actually doing this. That's exactly what we just did. Okay, give this one a try. So the combustion of propane gas, you can find this, this enthalpy, molar enthalpy value in the back of your book or in your reference sheets. Pause the video and give this one a try, and then we'll see if we get. Okay, so hopefully you've had a chance to give this a try. All right, so we're looking for delta HR once again, enthalpy change. We have a mass of propane with 15 grams. And the delta H for the combustion of propane, the molar enthalpy, if you look up that value, it should be negative 2220 kilojoules per mole. Right, so this is a reference table value. It's actually from Appendix C5, if you're looking up in the chart, the reference sheets chart. Okay, so really, we have to convert this into moles, right? So moles is mass over the molar mass, right? So propane is C3H8. So for our mole value, it's going to be 15 grams over, so 3 carbons plus 8 hydrogens, 44.11 grams per mole. Okay, and we have our delta H, that's our molar enthalpy. So delta HR is going to be my moles times delta H for the molar of combustion. So we're going to have, oh, I didn't do my answer to this one. Sorry about that. So the mole value you should get here is 0.3406. Oh, 006. My apologies. Look at that. My calculator. Okay, so the mole value is 0.34006 moles. Okay, so just a quick reminder, whenever you're doing multi-step problems like this, you never want to round this mole value. Okay, actually, anytime you're doing multiple steps, you don't want to round along the way. You want to keep, I would say, at least between 3 to 5 decimal points. You would never round this to 0.3. Okay, your delta HR value will be thrown way off as a result. And the more steps that there are and the more roundings that you do with each step, the further and further away your value will be. So we have 0.34006 moles times our negative 2220 kilojoules per mole, right? Mole cancels. And we should end up with a value. I'm just going to go straight to significant digits. So the only number we have here is 15.0, which is 3. So we should get a total of negative 755 kilojoules here for our final answer, right? So 1 mole worth of propane would give off 2,220 kilojoules, but we don't have 1 mole of propane. We have 0.34006 moles. So we adjust our kilojoule value accordingly.